Yeah, I'm Finnegan. I'm a first-year graduate student at Arizona State University. But today I want to talk about some work I did in my undergrad with Faye Dye, who just spoke. So as Professor Dye explained, there are a population of planets that exist that appear to be near conditions of mean motion resonance. One of the details of this that he did not address is that most of these appear to be near what we call first-order resonances, where the difference in the integer ratio that defines that resonant arrangement is equal to 1. So for instance, the inner planet might go around the star 3 times for every 2 times the next planet goes around. However, within this population of near resonant or resonant planets, there's a subpopulation that are engaged in higher order resonances, where the difference in the integer ratio is greater than 1. So take that same inner planet going around 3 times. This time, just imagine the next planet only goes around once. This would be a 3-to-1 second order resonance because the difference is 2 instead of 1. The archetypical example of this phenomenon is TRAPPIST-1, where the inner 3 planets form an 8-to-5-to-3 higher order triplet. And if you haven't checked out System Sounds, there's a really good sort of bunch of work online to try to sonify this beautiful system that you should look into. So systems like TRAPPIST-1 and TOI 1136, which Professor Dye just talked about, are shown to feature higher order mean motion resonances with librating resonant angles. We know there are examples where higher order resonances can definitively form. However, more broadly, there's also a population of planets that exist at least near these higher order resonances where we can't necessarily say for sure. And I want to talk about that population today. Large-scale models intended to study resonance formation have generally ignored this sort of second-order population. And the reason is because the strength of mutual interaction that governs resonance formation scales with orbital eccentricity to the order. And remember, eccentricity is a number between 0 and 1, so if you square it instead of raising it to the first power, it becomes much, much smaller, order of magnitude or even more smaller. And so generally speaking, people have sort of dismissed first or second-order resonances as being too weak to capture a pair of migrating planets together. But as I just showed you, there's some observational evidence that this occurs. Again, this is a plot of the period ratio the period ratio distribution from the Keller sample. Most of these like little bumps near resonances are for first order, but again, there's still some near 5-to-3, and as I showed before, this growing sample of young systems is showing more and more. I would postulate that this very weakness that I've described is exactly why second order resonances are so interesting, however. So in the case of TOI 1136, the E and F planet are engaged in a second order 7/5 resonance. But if you perform like dynamical evolution studies of the system, it looks like they're going to be the first to fall out of their current arrangement and may sort of contribute to a resonant chain falling apart over time, helping us explain perhaps why, oh, this entire chain of resonances might break over a long time scale, and we end up with this roughly not necessarily preferentially distributed near resonances distribution that we see today. So before that question can be answered, whether or not second order resonances are important to resonant disruption, we need to make sure they can actually form in the first place. And so to do that, we performed a large sample study of disk migration simulations using pretty standard disk migration prescriptions. One exception I want to highlight is that we study a broader range of disk surface densities than normal to try to represent sort of truncated or translational disks that may be important in smaller planet formation. And then relatedly, we also consider the possibility of Peter Pan disks, these disks that can exist for 10 million years or more, that may also be important for the slow migration processes that might be ongoing for higher order resonances. The big deal is we do find that second order mean motion resonances can be formed in our simulations. But again, I told you that this should be sort of a hard to do process, and so it's a good question to ask as to how this actually occurs. To answer that, I just want to take a look at, I want to slide too far, just one example from our simulation. This is just the semi-major axes of 7 planets that are migrating inwards. You can see their semi-major axes decrease. And when the semi-major axes sort of reach this flat point, or maybe a little before, that indicates that the planets have reached a condition of mean motion resonance. Their separations are constant because their period ratio becomes constant. And you can see that this chain over about 900,000 years produces roughly a whole set of first-order mean motion resonances of various kinds. So not that interesting. But I did highlight 2 lines in red, so maybe you should ask why. The interesting thing that occurs is when the last pair, the furthest out, captures into a first-order resonance, a wave of perturbations is sent through a chain. And this actually forces the second planet just slightly inwards. It's hard for me to see, but this line is actually dropping just a little bit. Now, this is a cool process for many reasons, mainly being because as the second planet migrates inwards over this period, all the other planets are also going to have to migrate a little bit inwards to maintain their resonant arrangements. But curiously, the inner planet doesn't. And the reason is because the inner planet is stopped at the inner disk edge. It's basically as far in as it can move. There's a torque reversal at that point. It can no longer get any further in closer to the star. So what this means is the period ratio between the first 2 planets has to decrease. And in fact, you can see that it does, and you can see that after a short period of decrease, they capture into the next available mean motion resonance internal to the 2-to-1 that they start at. And that is this 5/3 second order mean motion resonance. Now, one sort of interesting dynamical thing that might be going on here to explain what's happening is the process of capturing into mean motion resonance will excite planet eccentricities. And you'll notice that because the pair in red started in the, or entered a 2-to-1 resonance before disrupting and becoming this 5-to-3 resonance, it had some initial eccentricity to begin with. We believe this is probably important to the process of capturing second-order resonances. So to talk a little bit more about that, let me just say that this planet undergoes some quiescent evolution after all of that messiness I just showed you and ends up in this resonant chain arrangement that's somewhat like the ones Faye was showing earlier. You see that inner pair I've highlighted in blue is locked very deeply at below the 10 to the negative 4 level in a 5/3 second order resonance. Now, again, why is eccentricity perhaps important in the capture of second order resonances? Well, there's a small caveat for dynamicists. Again, all mean motion resonance capture events involve some eccentricity and need some eccentricity to sort of get going. First order resonances have been shown to be able to sort of create enough eccentricity during the capture process for capture to actually occur. This is just a toy problem here, and you can see on the left side that for any range of eccentricities that these planets enter with, there's 100% probability up to really high eccentricities that capture will occur for a first order case. But if you look on the other side, that's a second order 5-to-3 resonance. And you'll notice when eccentricities are too low, the planet cannot capture at all. It needs some initial eccentricity in order to facilitate the capture process and make capture probabilistic. Again, we believe that this breaking from a first order resonance and then entering into a second order resonance is perhaps the pathway to generate that eccentricity that you need. So again, sort of as an overview, second order mean motion resonances are most likely enhanced in eccentricity. And we actually see this in our simulations. The eccentricity distributions for different orders of mean motion resonance that come out of our simulations are statistically distinct. And second order resonances generally have higher eccentricities. Why does this matter? Well, to go back to our earlier point about disruption of resonant chains, enhanced eccentricities may be important in sort of disrupting resonances over time. The systems will become less stable over time, may be important, may cause resonance overlap, and ultimately result in secondary resonances being very rare. And there's an undergrad at Caltech who's been using my simulations and sort of integrating them forward in time and removing the disk to see how second order resonances are actually influencing the long-term evolution of systems. With the remainder of my talk, I just want to give two more quick findings from our initial study. As second order resonances are weaker, it was postulated previously that you can only sort of find a second order resonance if it just happened to start, the planets happen to start their migration very near that second order resonance position. But as I hope my example has demonstrated, that's not necessarily the case. And in fact, actually, if you dig into the cumulative distribution functions for the initial period ratios of planets engaged in different order resonances in our simulations, you can tell and you can determine this mathematically that they're statistically indistinguishable. That is, a 2-to-1 resonance, or planet ends up in a 2-to-1 resonance, may start well beyond the 2-to-1, but that planet could also end up in the 5-to-3 resonance and start with the same initial period ratio. The plot on the right is sort of just another way to show that. One other finding that I want to really highlight is, you'll note I haven't quoted the exact fraction of higher order resonances we find in our simulations versus first order resonances. And that's because we believe that's probably highly dependent on disk properties or that we prescribe. So, what is the range of disk surface densities we allow for in our simulations? We think is probably a little more robust is the observed fraction of individual mean motion resonances. That is, how common is the 5-to-3 resonance versus the 7-to-5? And earlier in this talk, I showed that there was a subpopulation of the resonant systems that appear to be near second order resonances. And I've just taken that data, and this time plotted it in blue for first and second order, and then in red are our simulations. And you generally see, with an exception that I'm happy to talk about if people have questions about it, that we have very good agreement between the final resonances that we see in our simulations and the ones that we see observationally. Most notably, there's a decrease in the incidence of resonance as you go to deeper and deeper resonances, and that's because the planets, which remember the Keller period ratio distribution, generally planets are forming somewhat far apart, they're going to have to migrate inwards past a bunch of different high strength resonances to reach, like, for instance, the 6-to-5 resonance. Okay, this work is on arXiv. It's been submitted to AppJ if you want to check it out. And while this is no longer my main focus, I have transitioned to working at Arizona State University with Luis Wellbanks. I want to say that our group still cares a lot about atmosphere's relation to planet formation, and I'd be happy to talk about that more if you have questions. Thanks.
Ilaria Pascucci, University of Arizona. Thank you very much for the nice talk. I was wondering if you can comment on what happened to these resonances when the disk is dispersed, so this inner edge doesn't exist anymore.
I will refer you primarily to one of Faye's other students who's using my simulations to study that right now. This is a future project that I have not done. I think that's the big question, though. I think that's the question is, like, to what extent are these resonances disrupted? We would expect, especially given that the second order ones generally have pretty high eccentricities, that they're going to break apart, and this sort of breaking the change approach is going to be recovered. Yeah. Mhm. I can hand you my mic.
Yes, I think the timescale of dispersion would be quite important there. If it disperses very, very slowly, it is possible to maintain the resonant lock. And that slow timescale is actually not, I think that it may not even be astronomically terribly slow. Okay. So resonances, generally, even second order resonances can be maintained in lock under a wide range of conditions. So the fact that we don't find them is very curious. And I think dynamicists, and you'll probably agree, dynamicists have been scratching their heads about broad distribution, the non-resonant ones. Where does that come from?
Right. And there are theories of planet formation that don't involve migration, right? So maybe we're just looking at the wrong picture here. I don't know. Other questions?
We do have one more over here.
Great.
Hi, thank you so much for talking about mean motion resonances. I love those. Can you go back to your result, like a couple of slides before? I'm not sure I really caught it. Yeah, the problem with the 3, 2, 1. So no, just a couple
More further back or further forward?
further forward, please.
Gotcha. There we go. Yeah.
This one. I'm not sure I caught what you were saying about the discrepancy between your simulated and observed, and I'm trying to understand with the 3, 2, 1. Can you please re-explain to my
So
brain?
I didn't explain the discrepancy in the 2 to 1 and the 3 to 1. And the general thought here is there's an observational bias issue potentially. There's a range of different ways you can think about this, but generally if you have a large period ratio, right, that would imply, that there's a good space between planets. But it turns out, if you're thinking again, our initial conditions that we initialize our period ratios are based on that Keller period ratio distribution. And it's very possible in the Keller period ratio distribution that we've missed some intermediate planets and systems that when you're calculating period ratios of adjacent planets would totally change the period ratio distribution if 2 planets that seem to be at a 2 to 1 resonance or near beyond 2 to 1 are actually got a planet in between them. And so again, our argument is that there are probably more planets that are starting really far out and catching into the 3 to 1 and the 2 to 1 than are actually physically out there. That makes sense.
Okay, yeah. No, I was just asking the question because I've already been confronted with the 3, 2, 1 that brought a lot of problems to me, and I was just wondering if you had any possible artifacts in the simulations, or no? Renu is saying like we've had enough. We'll discuss that later.
Okay, thank you. Yes, it's a big can of worms.